Hi everyone, I'm happy to meet all of you through this video lecture. This session will be a recap of what we already discussed in the last few classes about radiation heat transfer. As we know, radiation is one of the three modes of heat transfer, but it varies, it differs from other two modes of heat transfer in particular way. Radiation can be defined as the transfer of energy in the form of electromagnetic waves even without any intervening medium. So for conduction and convection heat transfer to happen, there should be medium, but radiation can happen even in vacuum actually. So that is one difference. Another difference is radiation is transmitted in the form of electromagnetic waves. A typical example of radiation exchange is the amount of energy what we receive from the sun. You know very well, between the sun and earth, it is only vacuum. So radiation transfer can happen in the vacuum also. There are some important terminologies in radiation heat transfer. We'll try to recollect since we already discussed in normal classes. So when a radiant energy is falling on a transparent surface, three things can happen. One is some of the energy may be absorbed by the surface, some of the incident energy may be reflected back, while the remaining portion is transmitted to the other side through the material. All these three can coexist. From this, we can define three properties: absorptivity, reflectivity, and transmissivity. We'll see one by one. So, absorptivity can be defined as the ratio of the amount of radiation absorbed by a surface to the total amount of incident radiation. Alpha is a notation for absorptivity. Reflectivity rho can be defined in a similar way as the ratio of radiation energy reflected by the surface to the total incident radiation. And transmissivity tau can be defined as a ratio of radiation transmitted to the total amount of incident radiation. So if we sum the three, you can understand that alpha plus tau plus rho must be equal to 1. It's a very important relationship from which we can try to calculate other property by knowing any two properties. And another important concept we already seen is black body. So a black body is defined as a body which can absorb all the radiation incident upon it. No reflection, no transmission. All the energy is absorbed. Such an idealized body is called black body. So we can easily say that absorptivity alpha for black body is always equal to 1 because no fraction is reflected or transmitted. Then another few important terminology is emissive power and monochromatic emissive power. Emissive power of a black body is defined as the amount of radiation energy emitted by a body per unit time per unit area. The unit is watts per meter square. Any black body emits radiation in the entire spectrum of wavelength, from the smallest wavelength to largest wavelength. At each wavelength, it will be emitting certain amount of radiation energy. we call that as monochromatic emissive power. So we can define monochromatic emissive power or spectral emissive power as the amount of radiation energy emitted by a surface at a given wavelength per unit time per unit area. The unit of monochromatic emissive power or spectral emissive power is watts per meter square per microns. Then another important law we are going to discuss, that is Stefan-Boltzmann law. Like Fourier law of heat conduction is the basic law for heat conduction, and Newton's law of radiation is the basic law for heat convection. Similarly, Stefan-Boltzmann law is a basic law for radiation heat transfer. It says the emissive power of a black body is directly proportional to the fourth power of its absolute temperature. Absolute temperature means the temperature expressed in Kelvin. So when we equate it, we get emissive power E suffix B is equal to sigma into Ts power 4. Ts is the absolute temperature of the surface, and sigma is called Stefan-Boltzmann constant. Its numerical value being 5.67 into 10 power minus 8 watts per meter square Kelvin power 4. It is a very important law. From this, you can find out the emissive power of any black body by knowing the temperature. Then we have an expression for monochromatic emissive power or spectral emissive power. So here is the expression for that. EB lambda is equal to C1 divided by lambda power 5 and E power C2 by lambda T minus 1. We have already seen that the amount of radiation energy emitted by a black body per unit time, per unit area and per unit wavelength is called monochromatic emissive power. This law is called Planck's law. EB lambda is monochromatic emissive power. Unit is watts per meter square, micrometer. T is absolute temperature of the black body, and C1 and C2 are constants, which you can read from heat transfer data book. Then we define gray body or real body. At any given temperature, gray body emits less amount of radiation than a black body can emit at the same temperature. So from this, you can define a new property called emissivity. Emissivity epsilon is defined as the ratio of emissive power of a given body or given real body or gray body to the emissive power of a black body at the same temperature. So this is called emissivity. So emissivity of black body is always 1 by the very definition of emissivity, while epsilon will be less than 1 for any gray body. From this you can write emissive power of a gray body is equal to epsilon into sigma into Ts power 4. So to have a better comparison between a black body and gray body, you can say for black body absorptivity alpha is equal to 1 because it absorbs all the incident radiation and it emits the maximum amount of energy at any given temperature. So from the very definition we can say emissivity of a black body is equal to 1. So both alpha and epsilon are equal to 1 for a black body, and as per Stefan-Boltzmann law, emissive power of a black body E suffix B is equal to sigma into T power 4. For gray body, absorptivity is less than 1 and emissivity is also less than 1, and its emissive power Eg is equal to epsilon into sigma into T power 4. That's why a black body is always called as a perfect absorber or perfect emitter. Then Kirchhoff's law is another important law. It says when two surfaces are in thermal equilibrium, emissivity is equal to absorptivity. That is, alpha is equal to epsilon. Sorry, this is not equal to 1. Simply alpha is equal to epsilon. Then Wien's displacement law. So this figure shows the variation of energy, that is our monochromatic emissive power with respect to wavelength. You can see that at any temperature of the body, the monochromatic emissive power becomes maximum at a given wavelength. Right? So when you increase the temperature, you can see that the lambda at which monochromatic emissive power becomes maximum gets shifted to the left hand side, that is towards smaller wavelength, right? And this Wien's displacement law says the product of the wavelength corresponding to the maximum emissive power of a black body and its absolute temperature T is a constant and equal to 2898 watts per 2898 micron Kelvin. That is lambda max multiplied by absolute temperature of a given black body is equal to 2898 micron Kelvin. So we have seen the basic terminologies related to radiation heat transfer. Please go through the video again and try to master it. We'll discuss the other things in the next video. Thank you. If you have any doubts, you please mail me. I'll be able to clear it in my next session.